So hello everyone. In this particular session, I'll be running a very simple code in order to explain how exactly SWI, that is software interrupt instruction, works. Okay. First let's check if there are any errors. No, so we'll proceed with debugging. Okay. So the very first instruction here is nothing but a sudo instruction which loads the address of start into PC, and you can see some comments here. Okay, what is this particular comment? It is nothing but we are defining each address here 048 is associated with routines of certain exceptions. Okay, that is 0 is the address which identifies as the address for reset handler. Okay, and then we have the address 8 here which is associated with software interrupt. Okay, and other information is provided, but you can see b space dot, which is nothing but an infinite loop. Okay, branch to itself happens here. Our focus will only be on reset part and the software interrupt part. What happens when I execute this? PC is updated with the address of start, which will make sure that the control will reach this particular instruction. Let's see that happening. Yes, so PC is updated with this address. The very first instruction you notice here is MSR. In my last session, I explained how MSR instruction works. That is nothing but this content, whatever is specified here, is updated in the CPSR's control field. Initially, the code had started working in supervisor mode. That is what happens anytime you run an ARM code in Keil. Okay, reason is this is nothing but a bare metal code, that is there is no OS used here, and every time on reset, okay, very first mode ARM enters is a supervisor mode. Okay, so unless any interrupts occur or you manually change the mode, it exists in supervisor mode. Okay, specifically when you run in Keil. Okay, this will be helpful if you continue running in supervisor mode because it helps you execute even privileged instructions. But when you execute this particular instruction, that is software interrupt instruction, you will anyway jump back to supervisor mode. I want to show that difference here. For that, I'm purposefully using this instruction to initially change my mode to user mode. Why is that the case? The last bits here 1 0. Okay, when this particular data is updated in the CPSR, mode change happens from supervisor to user mode. Okay, let's see that happening. Yes, currently you are in the user mode, which can only execute very simple instructions like move, add, etc. Okay, these are some random instructions I have considered. Okay, just to show that currently the instructions are executing in the user mode. So what I have done, I have just moved a content 5 into register arg0 and a content A into register arg1. So now I'm done with executing a few instructions in user mode. Now let's actually move into our actual software interrupt instruction. These numbers are not predefined. Okay, it depends upon what numbers you have associated with the services provided in your software interrupt handler. Okay, so for now just consider them as some random number, but what you should know is as soon as this instruction is executed, you will notice few change. First thing you will notice is nothing but the PC will be updated with the address 8. Okay, the reason it's updated with 8 is because in case of LPC2148, it's predefined that the software interrupt handler should be specified at address 8. Okay, so that is one thing you will notice. Next thing you will notice is there is a jump from user mode to supervisor mode, because the purpose of this instruction itself is to request some service from OS or to run supervisor code. Okay, so that you will notice. One more thing you'll notice is whatever is the content of CPSR will be updated in the SPSR of the supervisor mode. Along with that, the link register here will be updated with the return address. What is the return address? The exact next instruction to be executed in this particular sequence. Along with all that, The I bit of CPSR will be set to 1 to disable any low priority interrupt requests. Let's see all those changes happening. Okay, the I bit is set as 1 in the CPSR. If you check the mode, it has changed to supervisor mode. The link register is updated with the return address. The SPSR is updated with the previous CPSR content. Okay, and the PC is updated with the address 8. Okay, all these things have happened as one atomic operation. Okay, now let's see what happens here. We are trying to update PC with the address of SWI handler so that we can jump to that particular routine or that particular code. The very first thing I'm doing here is, now this is defined by me. Okay, what I'm doing here is, whatever is the content of R0 to R3, that is register R0, R1, R2, R3 along with link register, I'm storing it in the location pointed by the stack pointer. Now currently stack pointer is pointing at location 0, but you can see full descending, and I have already explained about full descending in a separate session. Okay, so I'll not go into depth of that, but I'll just inform you that all these contents are stored in the location pointed by stack pointer in the descending manner. That is, these contents, that is register R0, R1, R2, R3, LR is stored in this particular memory location. Okay, that is below 0. Okay, you can see updated memory content here. Okay, so those are the contents we have saved here by using store multiple full descending. Now here what I'm trying to do is nothing but I'm trying to identify which particular service request is carried out. So how will I identify that? I already know link register has stored the address of the next instruction to be executed once we return. If we subtract that address by 4, I'll get my actual instruction. Okay, so that is what I'm doing here, and the result of that is stored in R12. So this is nothing but the address of this particular instruction. By using LDR, I'm loading my actual instruction into register R12. Okay, the content of R12 will be actually this particular instruction itself that is loaded into register R12. You can use some other register also. Okay, I have used the same registers here, and then I'm performing AND operation between R12 with the value 0, 0 and all F's. The reason for that is the last 24 bit represents the number. Okay, the initial bits here represent the instruction opcode, and if conditional codes are involved, all such information that is irrelevant to us. We just want to know what number is specified. So when ANDing is done, bit masking happens. Okay, when you AND anything with 1, why I'm saying 1, F is nothing but all ones, right? So this, when ANDed with R12, generates our desired service number. So we identify the service number, and then in my SWI handler, I have defined two services. Okay, service 1 and service 2. Okay, and based on what you have chosen, I'll compare the obtained result here R12 with the value 1. If it's actually 1, I'm branching to this particular service and performing some addition operation. At the same time, if in case this is not true and R12 has some value 2, that is nothing but if this was the request made, in that particular case I'm jumping to the second service I'm providing. And what is the service? I'm just performing addition here between R1 and R0, and here I'm performing subtraction, and in both the case I'm updating the CPSR register. Okay, so once all this task is done, I'm trying to reload whatever data was stored in the memory location back to the register R0, R1, R2, R3 and also to the link register, and then what will this do? That is move SPC, LR. Whatever is the content of LR is updated in PC. Why do we do that? So that we can jump back to the next instruction to be executed. Okay, and along with that, this particular instruction makes sure that the content of your SPSR, okay, is saved back into CPSR. Fine. Now let's see how exactly it works. Let's start with the first instruction. We are trying to perform subtraction. Okay, why is this done? To obtain the desired address. Okay, so as per this particular instruction, R12 is 2C, which means this instruction address is 2C. Next, what we are doing, we are loading actual instruction to register R12. So this is how our instruction is represented in the memory. Okay, and do I want the entire content? No, I want the last 24 bits. So AND operation will generate the value 1 as required. That is our actual service number. Now I'm comparing it with 1. In this case it is true, so it will branch to service 1. Why exactly this works? Because compare automatically updates the CPSR register, and because Z is 1. Why is Z 1? When equal values are there, now R12 is 1 and this value is 1, internally subtraction happens. So branch if equal is true and service 1 is to be executed. And what happens here? Addition. What are the values of R0, R1? It is 5 and A. When you perform addition, the result is nothing but F, which is stored in R3. Okay, and we are branching back to done. That is this particular step. Okay, and here we are restoring the values. If you notice here, as per this calculation, the value of R3 is F, but initially R3 was 0 before these instructions were executed. So as soon as you execute this, these values which we stored in the memory will be retained in the specified register. Okay, and along with that, when we go ahead with move S PC, LR, what will happen is our PC will now point back to this particular location. Okay, along with that, the CPSR is also updated with the original content which was stored in SPSR. Okay. So now we are again executing one more software interrupt instruction with the service 2 as specified. Okay, so what will this do? Again it will jump to vector 8. From there it will jump to your actual routine for software interrupt, and here stores the content of R0, R1, R2, R3 and link register in the memory. We are subtracting it to find the actual instruction address, which is this particular address, and then we are ANDing it with FFFF to obtain our required 24-bit value. What is it? It is nothing but 2. Now we are comparing if it is 1, no. So it will jump here to check whether it is 2. That is correct. So what exactly should happen? It should branch to service 2. So here subtraction is done, along with that updation of your CPSR is done. Okay, so this is the result of that, and here we have updated the CPSR. Once that is done, we are reloading whatever content was there in the memory back to our registers. And as you can see, R3 is now updated along with the link register, but CPSR is not updated. That happens when you perform this particular operation. Along with updating the content of PC with LR, it will also restore the CPSR content to the value it was before executing the software interrupt instruction. Okay, it was initially 0. Fine. So now we have just reached the infinite loop. So in this way, we have executed the software interrupt instruction, from where we jump to our SWI handler. We stored the required content, identified the service executed the service, and we came back. And all these operations are happening in the supervisor mode. But as you can see now, once you exited from this particular routine, your ARM mode is switched back to user mode.